But I'm just gonna get right back into it and just hope for the best. So let's get to it. Okay, so then we have 23. Um, Times 2 gives you 2 times 11 gives you 22. The remainder is 1. And then wait, I'm like losing track of myself now that we set up a box using the sequence of quotients as follows. Using the sequence of quotients, um, 2, 1, 11, and 2. So the quotients 2, 1, 11, and 2. The remainders. And for some reason, my brain is having a hard time with this time. Don't know why. But you put 0 and 1, and then 1 and 0, so like you flip the bits or whatever in these boxes. Then the rule to fill the remaining entries are as follows. And this is just like a weird like rule for how to do it. It's a bit confusing, but also self-explanatory. The new entry, you take the number at the top times the number at the left plus the number 2 spaces to the left. So the number here is 0. And that's the 2 leftmost stars are, this one's 2 because it's 2 times 1 plus 0. And this one's 1 because it's 2 times 0 plus 1. And so this is basically showing that what you've already done the extended Euclidean algorithm by hand. You've already divided this out. And now you take the quotients, you line them up in some sort of table, you have some sort of rules to follow, and you kind of just run through them step by step. So the textbook kind of walks you through how to get the 3 and the 1 and the 35 and the 12 and the 73 and the 25. So the completed box is right here. Look how pretty that is. And the last column represents A and B. This is what we started with, 73 and 25. And then here are the quotients. And then if you look here, 23, 2, 1, and 0. I guess we don't get the remainders. One thing that's left out. The value next to the last column gives the value of negative v and u in that order. So usually we see u and v. So I wonder why the textbook decides to just awkwardly, I guess because they're just out of order. But it's saying that you get negative v and u. So 12 is your u. See, that's just confusing for me. It's a lot to have to memorize. The fact that, but it works out. It gives you your u and your v in a different way. So you get to use, you're doing the extended Euclidean algorithm by hand. Oh, is this the tabular method they were talking about? Nice. Okay, and here's like the full algorithm for it. So in general, if A and B are relatively prime, so they have to be relatively prime, and if Q1, Q2, all the way to Qt is the sequence of quotients obtained from applying the Euclidean algorithm to A and B, as in figure 1.2 on page 13. So again, you do the Euclidean algorithm, you get all of your quotients. So if we're talking about this question here, it seems like, and I could be wrong, so maybe I'll get my code out. So cargo run. So A needs to be larger than B. So 2, 3, 5, 7, 3, 5, 7, 3, 9, 7. Okay. So the GCD of 397 and 2 is 1. So they are relatively prime. So if A and B are relatively prime, and so I need to get the sequence of quotients. So basically, I need to alter my code here to spit out the quotients all the way through. And then I'd be able to, I guess I can do it by hand and figure out, like, as you divide it, what happens. That'd probably be a really good idea, actually. Just do it by hand. The entries in the box are calculated using the initial values. Okay, yeah. It gives you the initial values. And then, so basically it tells you how to code this, to be honest. Like, these are your initial values. And then for I is greater than or equal to 3, you use this. PI does this, QI does this. Oh, I have to stop streaming in 10 minutes. I have another meeting. So I guess I'm going to move to that soon and finish eating my breakfast, probably. I'll probably stop streaming at this point. I got through one section. So basically, we now know that the extended Euclidean algorithm, so AU plus BV should equal 1. And so we basically understand that this number and this number are relatively prime, right? These numbers here. So we know that you can multiply U and V to these two, right, in some way to also get 1. There is some unique U and V available. And so I do a few different ways. Then it also gives you the way here in page 16, it basically says, there's going to be some way I need to add this to my code from week 8 to be able to solve the question using the computer. And then to do it by hand, I can just write it out. So I'll try and do both this afternoon. I need to get to the modular fast powering algorithm for big ints. Proving is tough, but I think the proof is actually in the book. We just went through it, I'm pretty sure. Okay, stream quality is terrible today. I need to get to the mod stuff. Okay, so not bad for now. I'll start on modular arithmetic next time. I do have a few meetings. So in the afternoon, I'll start with modular arithmetic, and hopefully, let's see, we're on page 19 now. We need to go through mod arithmetic quickly. Fast powering algorithm, there it is. We go through primes, and then we go through powers and finite fields. And that's where we need to get to generators as well. So I think we'll probably skip 1.6, 1.7. So I'll probably be able to finish this afternoon. 1.4 is, about primes is not too bad. It's pretty good, like prime fields and all this fun stuff. But yes, modular arithmetic and the fast powering algorithm will be next time this afternoon. Okay, thanks.